Welcome to another deep dive into the world of physics. Today, we're going to be looking at a concept that's both mind bending and profound. It's Sakharov oscillations.
And it really makes you question what we think we know about the
You
universe.
know, it really does. It's almost like looking in a mirror and realizing your reflection might not be as stable as you thought.
Exactly.
So, today, we're diving into the work of Andrei Sakharov, a brilliant Soviet physicist. And back in 1965, he came up with this wild idea. What if the particles that make up everything around us, the protons and neutrons, could actually transform into their antimatter counterparts?
Sakharov, he wasn't just any physicist. I mean, he went on to win the Nobel Peace Prize. He was a deep thinker about the world and humanity's place in it.
Yeah, he wasn't afraid to challenge conventional wisdom. So before we go any further, let's make sure we're all on the same page here. So we all know about protons and neutrons, right? But those belong to a family of particles called baryons. These are the building blocks of matter, the heavy lifters of the particle world. And for every baryon, there's an antibaryon, its antimatter twin.
And that's where these Sakharov oscillations come in. This idea suggests that these baryons, which seem so stable and permanent, might not be so stable after all. They could, in theory, oscillate or flip into their antimatter counterparts.
I'm already feeling a little shaky about the solidity of the ground beneath me. So, to understand how this could even be possible, we need to talk about something called grand unified theories, or GUTs for short.
Right, GUTs are attempts to bring together all the fundamental forces of the universe under one grand theoretical umbrella. Think of it like this. You know how electricity and magnetism, they were once thought to be separate forces, but now we understand them as different aspects of the same fundamental force, electromagnetism. GUTs are trying to do that for all the forces, including the strong and weak nuclear forces, the forces that govern the behavior of particles at the subatomic level.
So, they're looking for the ultimate unifying theory of everything.
Exactly. And many of these GUTs predict something called baryon number violation, which is crucial for Sakharov oscillations to even be a possibility. It gets a little technical, but bear with me. Every baryon has what we call a baryon number. And traditionally, physicists thought that this number was always conserved, meaning it couldn't change.
Kind of like a cosmic accounting system where the books always have to balance.
It's a perfect analogy.
Yeah.
But GUTs suggest that this baryon number, it might not be absolutely rock solid. There could be very, very rare processes where this number isn't conserved, meaning baryons could potentially disappear or even transform into their antimatter counterparts.
So, like, there's a loophole in the cosmic accounting system.
Precisely, and that's what makes these Sakharov oscillations possible. But there's a fascinating twist. While baryon number, which we'll call B, might not always be constant, the difference between baryon number and another number we call lepton number L is considered to be a very firm symmetry.
Okay, hold on. Lepton number. I'm feeling a little lost here.
No worries. It's like adding another column to our cosmic accounting spreadsheet. Leptons are another family of fundamental particles, things like electrons and neutrinos. And they also have their own special number, the lepton number. And what physicists have found is that even if baryon number can change a little bit, the total difference between baryons and leptons always stays the same.
So it's like a cosmic balancing act. You can add or subtract from one side of the scale, but the total difference between the two sides has to stay the same.
Exactly. And this is where Sakharov's insight was so brilliant. He realized that even with this baryon number violation allowed by GUTs, this B minus L conservation, as we call it, still allows for the possibility of baryon-antibaryon oscillations.
Okay, that's pretty amazing. I'm still having trouble picturing how a baryon could just flip to an antibaryon. Like imagining a brick suddenly turning into its mirror image.
Yeah, it is a bit mind-boggling, isn't it? To understand this, we need to delve into the strange world of quantum mechanics. You see, baryons can indeed transform into their antiparticles. Then the particles we observe, those protons and neutrons, they're actually in a kind of blurry in-between state. They exist as what we call quantum superpositions of both baryon and antibaryon states.
Quantum superposition. That's where things get really weird, right? Like that famous thought experiment with Schrodinger's cat, where the cat is both alive and dead at the same time until you open the box.
Yeah, it's a great example of how counterintuitive the quantum world can be. So because of this superposition, a neutron for you, it exists in this blurry state of being both a neutron and an antineutron at the same time. And this blurriness is what allows it to flip between the two. It's this mixing of states that allows for the possibility of oscillations.
Okay, my mind is officially blown. But there has to be a catch, right? If this were happening all the time, wouldn't we notice things randomly disappearing and reappearing as antimatter?
You're absolutely right. That's the thing about Sakharov oscillations. If they exist, they're incredibly rare and ridiculously difficult to detect. The probability of a baryon suddenly becoming an antibaryon is incredibly tiny.
So, how could Sakharov have even come up with this idea if it's so unlikely? And more importantly, how on earth would we even begin to look for these oscillations if they're so rare?
Those are great questions, and they lead us to the heart of the mystery. It's like trying to find a single grain of sand that's different from all the others on an entire beach. But like any good detective story, we need to examine the clues. And in this case, the clues are subtle but potentially groundbreaking. So you're wondering how Sakharov even thought of this crazy idea, and how could we even find evidence for it? Well, it all comes down to the subtle clues, these tiny whispers that these oscillations, if they exist, might leave behind.
So, how do we even begin to search for a whisper that quiet?
Well, one place to look is inside the very heart of matter, within atomic nuclei. So imagine a neutron nestled inside the nucleus of an atom, seemingly stable and content. And then, in an incredibly rare event, it oscillates into an anti-neutron. What happens next? Chaos. The anti-neutron immediately annihilates with another particle in the nucleus, releasing a burst of energy that tears the nucleus apart.
Wow, talk about a dramatic clue. It's like a tiny nuclear explosion happening inside an atom. So, I guess scientists are looking for those telltale bursts of energy.
Exactly. And to do that, they built some of the most incredible sensitive detectors imaginable. Massive underground facilities, often housed in old mines, shielded from all the cosmic rays and background radiation that constantly bombards the Earth's surface.
Yeah, I was reading about these. They sound like something out of a science fiction movie. Gigantic tanks filled with ultra pure water or liquid argon, surrounded by thousands of super sensitive light detectors. It's hard to even imagine the scale of these things.
They are truly impressive feats of engineering. And you're right, they're looking for those flashes of light, the light that would signal a anti-neutron annihilation inside the detector. Like they built this incredibly sensitive net, hoping to snag even the faintest hint of these rare events.
But these detectors, they must be searching for other things too, right? Not just Sakharov oscillations.
Oh, absolutely. Multi-purpose. They're also on the hunt for things like dark matter particles. You know, those elusive bits of matter that we know must exist based on their gravitational effects, but which we've never directly observed. And they're looking for signs of proton decay, another process predicted by some Grant unified theories, where a proton seemingly stable forever suddenly decays into lighter particles.
So even if we don't find Sakharov oscillations, these detectors could lead to other groundbreaking discoveries. It's a win-win for science.
Precisely. And, it's important to remember that even null results, where we don't find what we're looking for, are valuable. They help us narrow down the possibilities, refine our theories, and focus our search in new directions.
That makes sense. It's all part of the scientific process, right? Constantly testing, refining, and pushing the boundaries of what we know. Are there any specific projects or detectors that we should be keeping an eye on in the future?
There are quite a few exciting projects in the works. One is the Deep Underground Neutrino Experiment, or DUNI for short. It's currently under construction in the United States, designed to study neutrinos, those ghostly particles that can pass through almost anything, but it could also have the sensitivity to detect those anti-neutron oscillations we were talking about.
DUE. Okay, I'll have to remember that one. Are there any others on the horizon?
Definitely. There's also the Hyperkamiokande experiment in Japan. It's essentially a supersized version of the already impressive Super Kamiokande detector. Just imagine a gigantic tank filled with over 260,000 tons of ultra-pure water surrounded by an array of incredibly sensitive light detectors.
Wow, that's hard to even fathom. Sounds like scientists are going all in on this search for new physics.
They are. And that's because the stakes are so high. If we can find evidence for Sakharov oscillations, it would revolutionize our understanding of the universe. It would mean our current models of particle physics are incomplete, potentially opening the door to new theories and even new fundamental forces.
Oh, it's amazing to think that something so tiny, so seemingly insignificant as a single neutron fitting into an antineutron, could have such profound implications for our understanding of the universe.
It really speaks to the interconnectedness of everything in the cosmos, how the smallest of events can ripple outwards to affect the largest scales. But there's another connection to the universe as a whole that's worth exploring, and that's the link to the very beginning of time itself, the Big Bang.
So we've talked about what Sakharov oscillations are, and these incredible lengths scientists are going to try to find them. It's a mind-boggling concept. But you mentioned this connection to the Big Bang. So how do these tiny oscillations relate to the birth of the universe?
Well, that's a great question. And it takes us to one of the biggest mysteries in cosmology. the matter-antimatter asymmetry problem. You see, according to our current understanding of physics, the Big Bang should have created equal amounts of matter and antimatter.
But wouldn't that mean they would have just annihilated each other, leaving nothing but a sea of energy? Like, poof, no universe, no us.
Exactly. And yet here we are in a universe dominated by matter. So where did all the antimatter go? It's a puzzle that's been vexing cosmologists for decades.
Okay, I see the problem. But how do Sakharov oscillations fit into all of this?
Well, Sakharov was brilliant, not just for proposing these oscillations, but for connecting them to this matter-antimatter conundrum. Remember those three conditions he laid out for baryon number violation, the loophole in the cosmic accounting system? He suggested that those same conditions could have been at play in the very early universe.
Hmm.
During the Big Bang itself,
So you're saying during those initial moments when the universe was incredibly hot and dense, these oscillations could have been happening much more frequently, and that tilted the balance ever so slightly in favor of matter.
precisely. If just a tiny fraction more matter was created than antimatter, that would be enough to explain why we see a universe dominated by matter today. The rest would have annihilated, leaving behind the matter we see and the energy that pervades the cosmos.
It's amazing to think that those incredibly rare oscillations, if they exist, could hold the key to understanding why we even exist, like a cosmic echo of those very first moments of creation.
What's even more remarkable is that Sakharov proposed this idea back in 1965, long before we even had the technology to begin to search for these oscillations. It really is a testament to the power of theoretical physics to probe the deepest mysteries of the universe.
So, as we wrap up this deep dive, what's the biggest takeaway you want our listener to walk away with?
Well, I think the most important thing is to hold on to that sense of wonder and realize that the universe is far stranger and more complex than we often imagine. Sakharov oscillations, if they're ever confirmed, would be a revolution in our understanding of the cosmos. But even if they remain elusive, the very act of searching for them expands the boundaries of human knowledge and inspires us to keep asking those big fundamental questions about the nature of reality.
It's been an incredible journey into the world of theoretical physics. We've delved into the heart of matter, explored the mysteries of the quantum world, and even touched upon the origins of the universe itself. But before we go, I want to leave you with one final thought. If those protons and neutrons that make up everything around us, from the stars in the sky to the ground beneath our feet, aren't truly stable, and can, however, rarely oscillate into their antimatter counterparts, what does that tell us about the ultimate fate of the universe? Could those tiny quantum fluctuations eventually lead to the undoing of the cosmos? A kind of reverse Big Bang. It's a question to ponder as we conclude our exploration of Sakharov oscillations, a journey into the heart of one of the most profound mysteries in modern physics.